We are going to discuss the results of our heat exchanger simulation challenge. The objective of this project was to simulate and evaluate a previously designed shell and tube heat exchanger using Aspen Plus, Aspen ISIS, and Aspen EDR. Our main purpose was to evaluate and validate the manual design and compare it with the EDR rating, checking if the exchanger satisfies the required heat duty, outlet temperatures, pressure drop limits, and installation restrictions. In this challenge, the exchanger is used in a phosphoric acid processing plant located in Altamira, Tamaulipas. Its function is to cool a phosphoric acid water stream from 90 Celsius degrees to 40 Celsius degrees using a water ethylene glycol service stream. This is important because the exchanger helps maintain safe operating conditions, protects downstream equipment, and allows the acid stream to be handled properly before storage or production. From my point of view, the first important argument is that the context of the process directly affects the exchanger selection, since phosphoric acid can be corrosive and may cause fouling. The exchanger cannot be evaluated only by heat duty. It must also be analyzed in terms of material compatibility, maintenance, pressure drop, and mechanical resistance. That is why the shell and tube exchanger is a suitable option for this industrial service. Now that the process context is clear, my classmate Les will explain the thermodynamic model and why property estimation was important.
Thank you, Meli. For the thermodynamic model, we use Carlson's decision tree to select an appropriate property method. Since both streams are liquid and polar mixtures, the model selection was especially important. For water ethylene glycol, NRTL is appropriate because it is a non-polar electrolyte mixture, and for phosphoric acid water, an electrolyte model will be more rigorous because phosphoric acid behaves as an electrolyte in aqueous solution. However, NRTL was used as a working method to maintain consistency in the property estimation and to compare it with the ideal method and the Alfa Laval data. My main argument is that property estimation is one of the largest sources of uncertainty in this project. The water ethylene glycol steam showed good agreement in thermal conductivity and heat capacity. For example, the thermal conductivity was very close between the manual data and Aspen, and the heat capacity was also similar. However, the phosphoric acid water stream showed larger deviations, especially in density, viscosity, and thermal conductivity. These tell us that the simulation results must be analyzed critically. If Aspen predicts properties that are very different from Alfa Laval data, especially for the acid stream, then the design may be affected because density, viscosity, heat capacity, and thermal conductivity directly influence heat transfer and pressure drop. So I agree with Meli that the process context matters, but I would add that the reliability of the simulation depends strongly on the selected property method. After understanding the thermodynamic model and property behavior, Beto will explain the heater and cooler block results.
Thank you, Les. The heater and cooler blocks were used to calculate the energy requirements of each stream separately before evaluating the complete exchanger. The heater block represents the water ethylene glycol stream being heated from 25 degrees to 35 degrees. In the ideal model, Aspen Plus gave a duty of 3.7209 multiplied by 10 to the power of 6 kilojoules per hour, while Aspen HYSIS gave 3.7021 multiplied by 10 to the power of 6 kilojoules per hour. These values are almost the same, which show us that both simulators reach the same heating target. For the NRTL model, The heating duty was also close to the ideal results. This means that changing the property method doesn't mean significantly change the heating requirement for the water ethylene glycol stream. On the other hand, the cooler block represents a phosphoric acid water stream being cooled from 90 degrees to 40 degrees. The negative duty in the cooler means that the heat is removed from the acid stream. My argument is that the heater and cooler blocks validate the energy balance before connecting both streams in one heat exchanger. Since both Aspen Plus and Aspen HYSYS reach the required temperature targets, we can say that the basic thermal load was correctly defined. I also agree with Les that the property method can affect the values, but in this part, the general heating and cooling requirements remain stable. Now that the individual energy requirements were checked, Brenda will explain the HeatX and Aspen EDR rating results.
Thank you, Beto. The HeatX blocks represent the complete heat exchange between the hot phosphoric acid water stream and the cold water ethylene glycol stream. In Aspen Plus, the hot stream was cooled from 90 to 40 Celsius degrees, while the cold stream increased from 25 to approximately 34.81 Celsius degrees. In Aspen HYSYS, the hot stream left at approximately 39 Celsius degrees, while the cold stream reached 35 Celsius degrees. The result shows that the heat exchange satisfied the main thermal objective of the challenge. Then, Aspen EDR was used to evaluate the exchanger with more detailed geometry, mechanical, and hydraulic calculations. The EDR showed an overall length of 4.83 meters at a field weight of 4,939 kilograms, which are both within the installation limits. The maximum available length was 6 meters and the maximum floated weight was 20 tons. So the proposed design satisfies the space in and weight restrictions. My main argument is that Aspen EDR validates the manual of our last class of heat exchangers design. The heat duty for our last course was 1041.66 kilowatts, while Aspen EDR predicting 1065.7 kilowatts. These values are close. And this means that both methods follow the same thermal performance trend. The tube side outlet temperature was also the same, 40 Celsius degrees, and the main difference appears in the mechanical and hydraulic results, such as velocity, pressure drop, and weight, because EDR performs a more detailed rating. And I also agree with Alberto that the energy balance was consistent, and EDR confirms that the geometry is also feasible. Finally, Leonardo will compare the alternative design and give the final interpretation of results.
Thank you, Brian. As an alternative to the shell and tube exchanger, we also evaluate a plate heat exchanger. The EDR results show that this alternative required 73 plates, an effective heat transfer area of 36.9 square meters, and a held field weight of only 363.3 kilograms. It also had a higher overall heat transfer coefficient, which means that the plate heat exchanger is more compact and thermally efficient than the shell and tube exchanger. However, my argument is that the most efficient option is not always the best industrial option. Even though the plate heat exchanger has a lower weight and higher heat transfer coefficient, the shell and tube exchanger may still be safer for this case because phosphoric acid can be corrosive and may cause fouling. So shell and tube exchangers are usually more robust and easier to maintain in the main industrial conditions. In general, our results show a clear pattern. The thermal performance remained consistent between IQ 2008B, our last course, and Aspen EDR, but the hydraulic and mechanical variables change more because EDR uses more detailed geometry-based calculations. The main uncertainty came from property estimation, especially for the phosphoric acid water stream. To conclude, our manual shell and tube design was validated using Aspen Plus, Aspen HYSYS, and Aspen EDR. The exchanger achieved the requirement cooling of phosphoric acid from 90 Celsius to 40 Celsius degree, stay within the pressure drop and installation limits, and show similar heat duty compared with the manual design. Therefore, the shell and tube exchanger is a technically suitable and robust option for the process, while the plate heat exchanger remains a feasible, compact alternative.
I agree with Leonardo because the plate exchanger looks very efficient, but for this process, the acid behavior is a key factor.
Yes, and that connects with the property comparison. The largest uncertainty was found in the phosphoric acid water stream, so the Alpha Laval data was important as a reference.
Also, the heater and cooler blocks show that the energy requirements were stable, which supports the thermal part of the design.
And the EDR confirmed that the exchanger geometry works within the installation restrictions, even with some difference for our last course.
Exactly, that is our final decision, is that shell and tube exchanger is valid and remains the safest design for this industrial application. Thank you for your attention.